Hey everybody. It is our last standard for our matter and chemistry unit, and this standard is all about atomic structure and the periodic table. So let's get to it. So we've been talking a lot about atoms, especially when comparing and contrasting our elements and compounds and mixtures. But we're now going to look into these subatomic particles that make up an atom. And so we're going to look at three. We have our electrons, protons, and neutrons. This is a Bohr model. It's just the name of the type of model of this atom. And you can see that the protons and neutrons are located in the center. That's where you'll always find them, and that's called the nucleus. Most of the mass of an atom is found here in the nucleus. The electrons orbit the nucleus and weigh a lot less. And we'll talk about atomic mass in a couple minutes. Now, this is a gumdrop model, but this can still represent an atom. You're going to see lots of different types of pictures, and what you need to do is interpret, what is this part in regards to an atom? So the center gumdrop is the nucleus of protons and neutrons, where these surrounding gumdrops are the electrons orbiting the nucleus. Each subatomic particle has a charge. Our electrons are negative, protons are positive, and there are no charges for our neutrons. They're what we call neutral. So I have a silly way to remember these charges. I think if I'm making a pros and cons list, my pros are going to be positive protons. If I'm neutral in an argument, I'm not taking either side. I have no opinion, no charge, neutrons. Now last, if I get electrocuted, that's a negative experience. So electrons, negative charge. Like I said, silly, but it helps me remember the charges. Okay, so we have now some more examples of Bohr models of atoms, and we also have two element keys. So I want you to pause here for a moment and see if you can come up with some similarities between the atom, the atomic structure, and what is labeled on the element key. Okay, so if you took a close look, you might notice, hey, look, the same amount of protons matches the atomic number. So there's 6 protons here. Carbon's atomic number is 6. There's 4 protons in this model. Beryllium has an atomic number of 4. That is because the number of protons determines the element that we are dealing with. Every element has its own specific atomic number, so no other atom will have 6 protons except for carbon atoms. No other atom will have 4 protons except for beryllium atoms. If the proton number were to change, it wouldn't be the same element. Element keys can tell us more information as well. They can tell us not just the atomic number or number of protons, but they also tell us the name, helium for this one, the symbol, as well as the atomic mass. The atomic mass is the average amount of the protons, neutrons, and electrons that make up this atom. Some even also give you the state of matter. Helium is gas at a room temperature, hence the balloon. Sodium, if you wanted more information about this element, look at the same details. Now, element keys can also tell us about the number of neutrons. So it gets a little tricky. Sometimes the amount of protons and neutrons are exactly the same, but sometimes they're not. So a trick to always know how many neutrons a pure atom of a certain element has is subtract the atomic mass and the atomic number. If I subtract 39.0983 and 19, I would get 20 if I were to round. The decimal, what's remaining over here, represents the electrons. They have such little mass. The majority of the mass is resulting from the protons and neutrons. We know there's 19 protons. That gives us the information that 20 neutrons are left over to make up a pure potassium atom. Now, potassium's symbol is K. sometimes the symbol does not really match the name of the element. And that's because the element symbols are derived from Latin. They're not derived from English. And so medieval Latin describes potassium as kalium, believe it or not, and that's where the K is coming from. All right, now there are certain trends that we can use to interpret the periodic table. So if you look here where it says group or family, our groups, just like this vertical line, are our vertical straight down columns. Groups and families, they can be used interchangeably. All of the elements in a certain group or family have very, very similar properties. So for example, neon and argon and krypton have similar properties. Sodium, potassium, rubidium have similar properties. Potassium and calcium do not, even though they're right next to each other. What they are in, these horizontal rows, are known as periods. As you move from left to right in a period, there are certain trends. The atomic number increases. So if I wanted to know, what element came after, say, number 27, cobalt, I would know I would have to move to the right to find the next one that is higher, which is nickel. Another trend is reactivity. Reactivity actually decreases as we move from left to right. The elements over here on this side are highly reactive, meaning they're very unstable. They can cause some really intense explosion reactions, destruction. That changes as we move to the right side. These are our more stable elements. Certain groups have names. We have alkali metals, alkaline earth metals, transition metals, halogens, and noble gases. The elements in these families all have similar properties, every single one found in the family. When you design your website, you are going to be researching what the specific properties are for these families labeled here. Now last, one more trend of the periodic table is how it separates metals, metalloids, and nonmetals. When looking at a periodic table, there's like this little staircase that I like to call it because it looks like a zigzag line. And what it does is it separates our metals from nonmetals. Our metals, which are found over here, have a lot of similar properties, but the ones in the specific families will be the most similar. So these ones are typically all solids. They are ductile, meaning they can be made into wires. They are shiny with luster. They're malleable, meaning they can bend without breaking, as well as good conductors, meaning heat and electricity can easily flow through them. So copper and gold are great examples to think about on this side of the periodic table because, if you've ever been to one of those penny machines where you spin it and it changes into a new shape, our gold for jewelry has lots of luster. Now, on the other side of the staircase are our nonmetals. They are of very different properties from our metals. They can be solid, liquid, or gas. They're dull. They're not shiny. They're brittle or break easily, especially if they're in solid form. They are insulators, meaning that they do not allow heat and electricity to flow through them easily. Hydrogen is over here, but it's special. It does belong in a nonmetal. Now, the staircase is representative of this group called metalloids. You can kind of think of them as in the middle of metals and nonmetals. They share properties of each of the categories. But the main thing to take away from here is that the staircase divides the group into metals and nonmetals. As we participate in more activities, we're going to look at more details on the periodic table, but use this video at any time to help you with any of your products.